name is Andrea Sand. I'm a professor here at Aalto University, and here in this workshop I'll be giving a lecture about including radiation effects in atomistic modeling. So what I'll be talking about is...
Andrea showed how she used machine learning to calculate the damage done to structures in space, damage caused by cosmic radiation.
So these are 99% atomic nuclei. And out of those 99%, 90% of them are protons, 9% alpha particles, and 1% even heavier ions. Now, my lecture doesn't actually include a whole lot of machine learning. We use machine learning for interatomic potentials describing the interactions between atoms, but not currently so much for the other radiation effects. The atom that you see going into the material here first hits head-on with the blue one, and then the blue one hits head-on with the purple one, and then these green ones, they're just neighbors. In the end, if you do simulations of the radiation damage formation with these, you also get different predictions. We have 3 stages of cascades. We call these cascades when we have secondary, tertiary, and so on recoils. So we have an initial very rapid increase in the number of atoms that are displaced. And here you see it in motion. And you see it expanding kind of randomly, and then now you have vacancies and interstitials, but you see this big blob of everything in the wrong places. Time is not linear here. We're in picosecond regime right now, but it lasts for several picoseconds, and then slowly you see things disappear, and this is when they're recrystallizing. It's becoming perfect crystal again. And eventually, we're left with what we call the primary damage. So this is then what we want to simulate, and then this evolves on nanosecond to year time scales. Machine learning is allowing us to possibly capture and predict processes which are too complex for us to come up with simple analytical models that will give us correct predictions. Personally, I think we do need to remember that it may give completely wrong predictions as well. So when we lack a clear physical model, it's also sometimes difficult to evaluate whether the predictions, in particular if we extrapolate to new situations, so whether these predictions are accurate or not. And that, to me, is one of the major things that we need to take care of when using this in physics and, by extension, in chemistry.